The history of wave particle flip-flop. What is light? This question has haunted mankind for a long time, but systematic experiments were done by the scientists since the dawn of the scientific and industrial era, about 4 centuries ago. Around the same time, theoretical model about what light is made of developed. While building the model of a branch of science, it is essential to see that it is able to explain all the experimental observation existing at that time. It is therefore appropriate to summarize some observation to light that were known in the 17th century. The properties of light known in the time of included a. Rectilinear propagation of light, reflection from the plane and curved surfaces, refraction at the boundary of two media, dispersion into various colors, high speeds. Appropriate laws were formulated for the first four phenomena. For example, Snell formulated his laws of refraction in 1621. Several scientists right in the days of Galileo have tried to measure the speed of light, but they had not been able to do so. They had only concluded that it was higher than the limit of their measurement. Two models of light were also proposed in the 17th century. Descartes, in the early decades of 17th centuries, proposed that the light consists of particles, while Huygens, around 1650-60, proposed that light consists of waves. Descartes' proposal was merely a philosophical model devoid of any experiments or scientific arguments. Newton soon after, around 1660-70, extended Descartes' particle model known as corpuscular theory. Built it was scientific theory, and it was explained various known properties with it. These models of light as waves and as particles, in a sense, are quite opposite to each other. But both models could explain all the known properties of light. There was nothing to choose between them. The history of the development of these models over the next few centuries is interesting. Bartholonius, in the 1669, discovered double refraction of light in some crystal, and Huygens in 1678 was quick to explain it on the basis of their wave theory of light. In spite of this, for over 100 years, Newton's particle model was firmly believed that preferred over the wave model. This was partly because simplicity of the particle because of the Newton's influence on the contemporary physics. Then in 1801, Young performed his double slit experiment and observation interference fringes. This phenomena could be explained only by the wave theory. It was realized that diffraction was also another phenomena that which could be explained only by the wave theory. In fact, it was the natural consequence of Huygens' phenomena which could be explained through wave theory. Idea of secondary wavelets emanating from every point of the path of the light. This experiment could not be explained by assuming that light consists of particles. Another phenomenon of polarization was discovered around 1810, and this too can't be explained by the wave theory. Thus, the wave theory of Huygens came to be forefront and Newton's particle model went into the background. This situation again continued for almost a century. Better experiments were performed in the 19th century to determine the speed of light. With more accurate experiment, a value of 3 × 10 to the power 8 meter per second for the speed of light in vacuum was arrived at around 1860. Maxwell proposed his equations for electromagnetism, and it was realized that all electromagnetic phenomena known at that time could be explained by Maxwell's 4 equations. Soon Maxwell showed that electric and magnetic field could be propagated through empty space in the form of electromagnetic waves. He calculated that the speed of these waves arrived at the theoretical value of 2.998 into 10 to the power 8 meter per second. The close agreement of this value with the experimental value suggested that light consists of electromagnetic wave. In 1887, Hertz demonstrated the generation and detection of such waves. The establishment of the wave theory on a firm footing. We might say that while 18th century belonged to the particle model, 19th century belonged to the wave model of light. Vast amount of experiments were done during the period of 1850 to 1900 on heat and related phenomena, altogether different area of physics. Theories and models like kinetic energy and thermodynamics were developed, which quite successfully explained the various phenomena except one. Everybody has a temperature emits radiation of all wavelengths. It also absorbs radiation falling on it. a body which absorbs all the radiation falling on it called black body. It is an ideal concept in physics like concepts of point mass or uniform motion. A graph of intensity is a radiation emitted by a body versus wavelength is called black body spectrum. No theory on those days could explain the complete black body spectrum. In 1900, Planck hit upon the novel idea. If we assume that he said that radiation is emitted in packets of energy instead of continuously as in a wave, then we can explain the blackbody spectrum. Planck himself regarded these quanta or packets as a property of emission and absorption rather than the light. He derived these formula which agreed with the entire spectrum. This was confusing mixture of wave particle as well as particle picture. Radiation is emitted as a particle, it travels as a wave, and again absorbed as a particle. Moreover, this put a physicist in dilemma. Should we again accept the particle picture of light just to explain one phenomena? Then what happens to the phenomena of interference and diffraction which cannot be explained by the particle model? But soon in 1905, Einstein explained the photoelectric effect by assuming that the particle picture of light. In 1907, Dibbe explained that the low temperature specificity of solids by using the particle picture of lattice vibration in crystalline solid. Both these phenomena belonging to the widely diverse area of physics could be explained only by the particle model, not by the wave model. In 1923, Crompton's X-ray scattering experiment from atoms also went in favor of the particle picture. This increased dilemma further. In 1923, physicists faced with the following situations. There were some phenomena like rectilinear propagation, reflection, refraction which could be explained by either by the particle model or wave model. There were some phenomena such as diffraction interference which could be explained only by the wave model, not by the particle model. There were some phenomena such as blackbody radiation, photoelectric effect, and Crompton scattering which could be explained only by the particle model, not by the wave model. Somebody in these days aptly remarked that the light behaves in particle on Mondays, Wednesdays and Fridays and as in wave on Tuesday, Thursday and Saturday. We don't talk on light on Sundays. In 1923, de Broglie with theory of wave-particle duality, in which he said that not only photons of light but also particles of matter such as electrons and atom possess dual character. Sometimes we be like a particle and sometimes as a wave. He gave a formula connecting their masses, velocity and momentum, deviation and particle characteristics with the wavelength and frequency wave characteristics. In 1927, Thomson and Davison and German in separate experiments showed that the electron did behave like waves in a wavelength which agreed with the given by de Broglie formula. Their experiment was on the diffraction of light through the crystalline solid, in which the regular arrangement of the atom acted like grating. Very soon, diffraction experiments with other particles such as neutrons and protons were performed on these two conformed with the de Broglie formula. This confirmed wave-particle duality as an established principle of physics. Here was a principle physicists thought which explained all the phenomena mentioned above, not only for light, also for so-called particles, but there was no basic theoretical foundation for the wave-particle duality. De Broglie's proposal was merely a qualitative argument based on symmetry of nature. Wave-particle duality was best a principle, not an outcome of a sound fundamental theory. It is true that all experiments whatever agreed with de Broglie formula, but physics do not work on that way. On the one hand, it needs experimental confirmation, while on the other hand, it also needs sound theoretical basis for the model proposed. This was developed over the next 2 decades. Dirac developed his theory of radiation about 1928, and Heisenberg and Pauli gave it a firm footing in 1930. Tomonka, Schwinger, and Feynman in late 1940s produced further refinement and cleared the theory of inconsistencies which were noticed. All these theories mainly put a wave-particle duality on a theoretical footing. Although the story continues, it grows more and more complex and beyond the scope of this note. But we have We have here the essential of structure, what happened, and let us the satisfied with it at the moment. Now it is regarded the natural consequence of present theory of physics that electromagnetic radiation as well as the particle of matter exhibit both wave and particle properties in different experiments and sometimes in the different parts of the same experiment.